Okay, it'll be, and you can look back over it if you want to, the downstream. It'll be after, and it takes a little while. It's a pretty long file because it's going to be 50 minutes, but it takes a while for it to record. So it'll be a little bit later on today before it'll be available. Okay, if you want to see it. So let's get going. Hi, we're finally reaching, we've been in the semester up to this point, and we're just getting to the fundamental theorem of calculus. It's kind of special. But it does show up in section 5.3, and that's what I'm going to be talking about in just a minute. One of the key things, I tell you what, let me move there immediately to the definition, what it's actually saying, the words of the second part, okay? So what I want to do is screen share with you this. Hey, when you guys see that, do you see a plus and minus on the side, or is it just plain? It's just plain? Okay, good. Notice the words here in the fundamental theorem. It's an important part of the deal. F, lowercase f. Big difference between lowercase and uppercase. If you use upper or lower wrong now, it matters, really different. But the idea is if lowercase f is a function, it's continuous on a closed interval a to b, closed is important. If cap f is any antiderivative of lowercase. So cap f is representing the bit, antiderivative, it's going up, that situation. If any antiderivative on AB, then the integral of f of x dx, little f of x dx, is equal to the antiderivative with b plugged in minus the antiderivative with a plugged in. Okay, and notice you guys, the one key point is this. I'm going to repeat this later on, but the idea is that little f, if you take the antiderivative in general, remember I've been talking about there being a plus c, because there's a constant that's being added to this. Any constant, when you take the derivative, it goes away. So it could be any constant, but it's the same cap f. That means the same c is showing up for both cases. Cap f of b has a plus c, and cap f of a has the same plus c, and you're subtracting it. So the c's cancel. So if you're doing a definite integral, you don't have to do the plus c. It's just the base core of the antiderivative, and you don't have to do the plus c, and it goes away. And I'll do a couple of examples of that right now, okay? Any questions up to this point? Okay, let's go to my iPad, and let's go to, all right. I've got a couple of problems here. Let's get this down. What am I doing here? Let me get out of that. Okay, so let's start with a basic. If you're integrating a constant, okay, is the function. I'm talking about the function little f of x over here on the side, over here underneath the graph. Little f of x is equal to 2. That's the function. All right, and over here I'm going to take the antiderivative of it. It's a definite integral because I've got specific start point and a specific end point. That's makes it definite. If that was open, then and it wasn't a from to, then that an a and a b, then that means you do need the plus c because there's no subtraction going on. There's no cancellation. But this situation, when we take the antiderivative, remember what we're doing. We're getting the area under the curve. You know, that's a part of the moment that we were dealing with. So let me remind you of this. Let's tell you what, go back to me again. Let's go back to me. All right, and recognize this. Are you guys able to see the screen here? Do you see the board behind me? Okay, so the idea was that when we did that first problem, we had velocity on the side, and we've got time down here on this side. That if velocity is the rate of change is on the curve, all right, then with the area under the curve turns out to be the amount of change that happened with whatever you're talking about. Distance over time is velocity. You know, how much time it took to go this far. Well, it turns out that the area under the curve, if the top is the rate of the change, if the function is the rate of the change, then the area underneath it is the amount of change of whatever the item is. There's a couple of problems in sapling that I'm asking you to do. Water is being poured into a reservoir. And they tell you the rate of change, the volume of water that's being put into it. It's a rate of change. Well, you take the integral of that, then the area underneath it is going to be, well, how many liters are in there? How many liters? You got a rate of change. How many liters are going in per hour? Well, it turns out the area underneath is going to be, that's how many liters it is. When you take the antiderivative, you get the actual value. There's another one, insects. How many insects? You're getting insects per day. It's increasing, population. Well, insects per day is the graph, is the function. Take the antiderivative, and the area underneath it is how many insects actually increase. That's what's going on there. So that's coming from the first part of the derivative. You notice that the part that I showed you a second ago, it said part 2. The part 2 is basically doing the calculations of the situation. So we're getting underneath the curve and finding this is actually the distance traveled, All right, so let's go back to my iPad and let's do a couple problems here. Okay, so we get, all right, so here's the deal. So we've got the integral. Notice what we've got. If this is a straight line, y equals 2x is a straight line going through 2. It's the line going through here forever in both directions, all right? I'm restricting it over here to between -2 and 3, all right? What's the area under that curve? Between -2 and 3, that's 2, that's 5 across here, and this is too high. So that means the area is 10. The area equals 10. All right, that means when we integrate this function over here, our answer should be 10. That's what we're calculating, the area under the curve down to the x-axis. All right, so what the rule says when we've got this thing, the integral of f of x from a to b dx is equal to cap f of b minus cap f of a. So we've got to figure out, in order to do this problem over here, do the definite integral, we've got to calculate cap f of x. And like I said, we don't have to worry about the c. So all it is, the antiderivative of the constant is stick an x on it. So cap f of x is 2x. Again, plus c if it's not a definite integral, but when we do this subtraction, the plus c goes away. So we end up with 2x. And look what happens here. So when I do the antiderivative of -2 to 2, -2 to 3, I'm going to get, and the notation, so we get 2x, and the notation that we've traditionally accepted, it's a little different what they say in the book. I'll tell you both of them. Typically, I've seen this used. I've never seen until this book what they've done in the text. This one I've shown going from just putting a bar back there reminds me of what A and B are. That's what the accepted notation is. Then that tells us B is 3 and A is 2. -2. All right? And that equals 6 minus, that's plus 4, which gives us 10, like we calculated up here a moment ago. Okay? So another notation that they use in the text is they put a bracket around the function completely like this, and then they put the A to B over here on the side. Don't worry about, if you want to do that, you're welcome to do that because you might see them do it, but I'm going to keep using the bar. It's a habit I've got, and I think it's easier, it's more efficient, and it's cool. All right? So that is kind of an important moment there. What do you think? Is that all right? The antiderivative, plug in B, plug in A, get the subtraction, and the answer is given. That is equal to, all right, now, get out your calculator if you would. Get out your calculator and take a look at it. I've got a TI-84 here, but it's set up right now as a TI-83 in a certain sense. So what I'm going to do is like what you would see on a TI-83. What do you guys have? Would you mind saying to me, what do you have? What kind of calculator? Just say 84 or 83.
84.
84.
84.
Good.
84.
84, 84. Okay, good. In general, you're going to see that if you have an 84, then you're going to see an integration bar show up when you do this problem on your calculator. So what I want to do right now is I want to do the integral of 2 from -2 to 3. So if you would hit math, the math key, then either space down to 9 or hit 9, and notice what you get there. You get f of n, the function fn int is what's down there, parentheses, that's what the indication. Well, in the TI-83, that's what I get on my next, instead of the integration bar, I get this. I'm gonna have to type it in. But what you've got is the integration bar. So what I want you to do if you've got a TI-84 is plug in the -2 down low, plug in the +3 up high, plug in 2 in the parentheses for the function, and then stick an x out there for the dx. That's a crucial part of it every time, okay? And hit enter and see what you get. See if it agrees with our 2, okay? On this function, if you've got a TI-83, you've got to write the function name down, then it's in terms of x, and then it's from -2 to 3, and that would give me what I've got here. That's 2, comma, x, comma, -2, comma, 3. Close parenthesis, enter, I get 10. Everybody agree? You see that? Okay, good. All right, now, let's do another one. Here's another point I want to make now. It's kind of important. We're gonna move through stuff kind of briskly. So I want you to be able to use the tool, use antiderivative, be able to use the fundamental theorem of calculus, and that's what this is saying. This is using the fundamental theorem to do that problem. Okay, now look, I want to do this one. Do this with me. I'm going to talk about the function. I've drawn a line here of the line x minus 2, y equals x minus 2. Notice the y-intercept is 2, slope is 1, so I go over 1, up 1, over 1, up 1. If I go over 6, I've gone up 6, etc. There's the function. Now, look, I want to get this area right here. The area between 2 and 6 for, well, look what's going to happen. Look what the answer should be, okay? This is up to 4. This is up to 1, 2, 3, 4. So this side is 4. 2 to 6 is 4. So 1/2 base times height, area equals 1/2 4 times 4, which is 8. Which is meaning if you do the integration of this function from 2 to 6, the answer should be 8. So in other words, I'm saying we're doing integral of 2 to 6 of x minus 2, traditionally in the parentheses, dx. The answer should be 8. Everybody agree? You get it? On your calculator? Make sure you do. Okay, here's the key point I want to make on this one. Look what happens when we do this over here. Notice it's under the x-axis. Key point being made. It's under the x-axis. And as a result, the circumstance is that it's going to be a matter of being, when it's under the x-axis, the result is negative. Anything under the x-axis is negative. And as a result, when we do this one, notice that this length is 2, this length is 2. So area equals 1/2 2 times 2. 1/2 of 4 is 2. So the area is equal to 2, and it's below the x-axis. So if you were ever asked to do a problem, what's the area of that triangle? The answer is 2. Area is not negative. But if you plug it into your calculator and you do 0 to 2 of x minus 2 dx, look what you get. I'm going to do it right now. You should have a negative sign in front of the 2, okay? So I'm going to do math 9. I'm going to do x minus 2, comma, x, comma, 0 to 2, comma, 0, comma, 2. Hit enter. You see, you get a negative sign in front of the 2. Notice that, okay? That is an indication that That area corresponds to this. Do one more with me now. And we'll do this one longhand also, okay? I want you to do 0 to 6 this time. Notice what you get. 0 to 6 of, so I've got the integrals, math 9. The function is x minus 2, comma, x is the variable, comma, and we're going from 0 to 6, 0, comma, 6, close parenthesis, enter. Do you get 6, which is the area above, which is 8, added to the area below, which is 2, 8 minus 2 is 6. So the calculator reads it as below is negative. If you're asked a word problem and you're asked to find out what the area of that triangle is, area is positive, okay? But if you're asked and you put it on your calculator, you're gonna get a negative number. So different problems go up and down, above and below the x-axis. And sometimes the below is gonna be subtracted off area, okay? That's gonna be part of the deal. Okay, so you get 6. Let's go with me now. Let's do it. I'm gonna do it longhand. Let's use the fundamental theorem of calculus from 0 to 6 of x minus 2 dx. Okay, so first I need to get cap f, which is the antiderivative of the term. So the antiderivative of x is x squared over 2, raise the power by 1 and divide by that same power, minus 2, it's a constant, attach an x to it, minus 2x. Traditionally, that's the function now, and we're taking that from 0 to 6. Okay? Now notice what we've got here. We've got, now we plug in 6, we got to do f of b minus f of a. Notice a is 0. X is in both terms. So both terms are going to be 0 when I plug in 0. But let's plug in 6 first. So I get 6 squared over 2 minus 2 times 6. That's f of b minus f of a. They're both 0, so I'm just going to put 0. Be conscious that if x is ever in the exponent, the answer's not 0. But in this case, they're both x's are down on the ground. That's 0. So that ends up giving us 36. That's 18 minus 12, which is 6. That's doing it longhand. Calculator to verify. So be able to do both, all right? So, like I was saying, get into Wiley Plus. I've given you 12, not Wiley Plus and Sapling. I've given you 12 problems. 2 of them are word problems, and they're problems that are giving you a formula that's giving you a rate of change. And it's asking you a question that means, how much change was there? Insect population. This is how fast they're growing. They're you know, how many are there? When you take the antiderivative, you get how many are there in a certain time interval. Same with liters of water, okay? That's that situation. Okay, so any questions at all about that? Okay, that's the general topic for today. It's going to be up to you to, if you want to stay on now, I'm going to go through exam 3. There's a few of you that did really wonderfully, and you've got all the answers already. You got pretty much the key. So you're welcome to stay if you want to, but don't feel like you have to. So it is a matter of now I'm going to go through the test, all right? So thank you for coming out. If you leave, don't feel funny. I'm just going to step on now and do the problems from the exam, okay? Any last minute questions? Okay, 5-3 problems. There's 12 of them in Sapling, okay? Make sure you get going on them, get squared away with those. All right, I'm going to go ahead and clear my iPad and go through the questions on the exam. Okay, so let me get the exam here. All right, the first question was saying, determine the following. And if you guys notice what the first question said, f of x was given to be, I'm up, okay, that's good. F of x equals x to the third minus 6x squared. This is one of those cases where it's important that you don't just assume you know what I'm asking without reading the question. This one said, include using the first derivative test for part A. There are a handful of you that didn't do that. Maybe a little more than a handful, okay? So it was important that you checked on each side of get the critical numbers by taking the derivative, check on each side to see if the slope is changing. That's the idea, okay? That's the first derivative test. So the situation here was we had to take the first derivative and go from there. So if f prime of x, the derivative is 3x squared minus 12x. And if I ever do something, oversee something, or if I have a typo, please speak up, everybody. If you're staying on, please feel free to say something, okay? All right, so this happened to a few of you on the test when you did the derivative right. Everybody got the derivative right. Then factoring it. If 3x is common, so that leaves x minus 4, okay? There were a couple problems that a couple of you did the factoring here incorrectly. Also, now when you find the critical values, there was more than one of you that left off the 0. When you set this equal to 0, you've got two values. You've got x equals 0 as one of the numbers, and a couple of you left off the 0. That was an important part of the problem to get that as a critical number. You left that off and you didn't get that. 0 and 4 were the two critical numbers. So it's a matter of drawing a number line, or that's the way I do it, to give indication. We're trying to figure out does the slope change between at the critical numbers. So, and the vast majority of you, not everybody, but several of you picked -1, 1, and 5. Those are easy numbers to work with. So that was what a lot of you did. So it's a matter of, we're trying to figure out what the slope is to the left, in the middle, to the right. Slope, that's f prime. So I got to plug this back into the f prime function. I need f prime at -1. I need f prime at 1. The values that are in between and on the outside, and I need f prime at 5. You could have picked 2 or 3 in the middle. The 2, it would have been worked just as good, or you could have picked a fraction also. But picking the easiest numbers to work with is most ideal. So let's do this. 3 times -1 squared minus 12 times -1 gives us 3 times +1 is 3 plus 12 is 15. That's positive. That's positive over here. So it's looking like this, going up. F of 1 now, 3, 1 squared minus 12 times +1 equals 3 minus 12 equals -9. That's negative. That's going down. So this is a max up there. Does meet. And then for 5, we've got 3 5 squared minus 12 times 5 gives us 75 minus 60 equals 15. Positive. That's positive here, going up. Therefore, this is a max because they meet down there. It changes from down to up to down. Both of them are maxes and mins, okay? So what we've just shown, what we're trying to answer the question is it local max, local min? So we can verify because of the fact that it changes from positive to negative at 0, therefore, we got to plug it in to find out what the value is. We got to find out the actual value of the coordinate. So we need to plug that back into the original function. That gives us 0 minus 0, which is 0. So the coordinates are 0, 0, and that is a local max. Or you could also say the local max is 0 at x equals 0. And then you've also got to figure out what it is at 4. And we're guessing, and we're seeing, we've just shown that it's a local min because it went from down to up. Local 4 gives us 4 to the 3rd minus 6 times 4 squared. 64 minus 96 is negative 32. So we got 4, negative 32. So local min at 4, negative 32, or local min is negative 32 at, whoops, at x equals 4. Okay, any questions on that at all? Anybody see anything different or any comment, anything to make? Okay, that's the goal of the first derivative test, is to find local max and local min. And local min came first, so make sure you look at the directions and follow order. So let's go to part B, which is saying increasing and decreasing. So now, if you use this, if you set this up right, then you show that it's positive over on this side. If you've got the graph and you went up there and you showed that it went from increasing to decreasing, then you show that it was positive here and negative here. And that indicates that for part B, this is 1A, 1B, you showed that it's an increasing function where it's positive, and that's happening here and here. And you did that on the first part if you did it, but if you didn't show that, if you didn't show that clearly, then you needed to go back in and make it clarify using information and not just the graph that it's increasing from here going out to negative infinity, and this is 0, and this is 4, and this is infinity. So increasing intervals are negative infinity up to 0. Open on each side, infinities always get open, but at the critical point, it's neither increasing or decreasing because it's at the top. So it's 0 there. So that means it's got to be an open interval. You don't include the point. And union with the far right, which is 4 to infinity. Okay, you show that it was increasing there. And decreasing intervals in between. It's going from here to here, both open again. Got to be open because it's not increasing or decreasing at the endpoints. Questions on that at all? Okay, good. Well, let's keep going. Again, please speak up if you got questions. I'm going to move on to a new screen so we can get on to 1C. Okay, so 1C was, okay, we had f of x, and if you showed your work elsewhere, you didn't have to rewrite this all the way out. But I took it off the screen here, so I'm going to put it up on here. That's the original function. Therefore, f prime was equal to 3x squared. And since we're talking concavity, that brings to mind second derivative. The second derivative test has to do with determining concavity. So the second derivative is equal to 6x minus 12. And this again is where a couple of you got the derivative, but then factoring bit you a little bit. So it's a matter of recognizing here, again, that 6 is common. So if you factored this out, you ended up with getting 6, and a couple of you got something other than 2 there, okay? You got a 6 or something of that kind of line. So it turns out that, so if we set that equal to 0, x minus 2 equals 0 is the only place where the second derivative is equal to 0. And that's a clue that that's where the point of inflection is equal to, okay? It's a matter of checking it to verify it, but that's where the point of inflection is happening. Our graph, again, we had looked like this. And we now know the point of inflection happens at x equals 2. And the question about concavity now clearly is answered. Several of you just pointed to your graph, and I said at the top again, just pointing to the graph isn't going to give you as much credit as showing your work and showing how you get it. So plugging in the second derivative test is plug in the critical points and find out the concavity there. You could pick other numbers too, but the second derivative test is plug in 0. So f double prime at 0 is actually equal to 0 minus 12, which is negative 12, which is negative. So this is negative over here. That means it's concave down. And f double prime at 4 is equal to 6 times 4 minus 12. That's 24 minus 12, which is 12, which is positive, which means that x equals 4, it's positive, so that means it's concave up. All right? So the interval is concave down. Dave got a little bit strange there. Concave down. I put concave up first. So I add concave up first. Up is equal, the interval is, now this is where you've got to make sure, a couple of you picked the critical point for your endpoint. And it is concave up all the way to it till it changes the concave down. That's at the point of inflection. So right there, you've determined that right here. X equals 2 is where it's going to. So concave up from 2 to positive infinity. Again, open interval, because at 2, it's neither, it's changing, switching over. And concave down from 2 to the left to negative infinity. Okay? So that's the answer to 1C. And I wanted you to show your work doing the math of how you actually showed it was concave up and down, okay? And if you didn't use the second derivative test, you could have pointed to the fact that it changed from negative to positive, or positive to negative, and therefore it was concave up or down, or however you wanted to do that. But this is the most straightforward way to do that. Any questions on that at all? All right, 1D. 1D was what's the point of inflection? And that we just determined a second ago. And as long as you showed your work somewhere, I accepted it. Actually showing it's a point of inflection is actually saying, and very few of you did it, so I didn't count this, but it's you verify that it's a point of inflection by knowing that it changes sign there. It's concave down to concave up, or concave up to concave down. That indicates that it's a point of inflection, okay? And the point of inflection occurs at f of 2, which turned out to be 2 to the third minus 6, 2 squared, which is 8 minus 24, which is negative 16. So the coordinates end up being 2, negative 16. Questions on that at all? Okay, let's keep moving because I want to get through all of them before the end of class. And I'm going to go to number 2 then. No questions at all. Fantastic. Hope you guys are smiling. It's overcast here today. It was wet this morning and it was kind of cool. So it was a wet cold, and that's not fun always, but. Okay, let's go on to number 2. New function, number 2. All right, the function is find absolute minimum and maximum. Find absolute maximum and minimum for f of x equals x to the third minus 3x squared plus 20. Okay? Now, one of the ideas here is that you got to find the max, absolute max and min. So getting a sense of what the graph kind of looks like, knowing that it's a cubic and it's got things in the middle, it's got terms, an x squared or an x term in between, you know x cubed is coming up and going up, and it's got that stuff in the middle. So it's something like this somewhere. It's going to be like that. Okay? So the idea is absolute max and min. Part of the deal is you've got a closed interval this time. That's it. This doesn't have an absolute max or absolute min. But when you limit it from -2 to 2, now the extreme value theorem says there's got to be a max and there's got to be a min. It can't be going to infinity in between there. If it is, it's not polynomial. It doesn't work. Okay. So the thing you got to check on this, remember what you've got to do. You've got to check the endpoints and any critical values in between where you might have a possible high and a low, and that's going to happen where the slope is equal to 0. That means you take the first derivative, set it equal to 0, find critical numbers, and if there's any between the endpoints, you check the endpoints and those critical numbers. That's it. So I'm going to, and several of you just listed all the points in between. I took a little off of that. You're going to have problems downstream that are going to be massive. And I'm just saying to you, yes, it wasn't absolutely wrong, but I didn't take off a great deal if you did it. But if you counted every integer in between and checked them all, I took off a little bit. That's not what the system that we were talking about doing in class. You just check the endpoints and the critical numbers in between. That's it. All right? So we need to first find the critical numbers. Take the derivative and set this equal to 0. 3x is common, and we get x minus 2 back. Okay, so that gives us 3x, and there were a couple of you again that lost the x equals 0. You only did the x minus 2. You got to do both. So those are our critical numbers. So we've got to check the endpoints, and one of the critical numbers is the endpoint. So it's not overkill. We don't have to do an extra thing, but this 0 is a critical number in between. So we need to check the endpoints and this critical number in the original function and find out which is the highest and which is the lowest. So we've got to do the f of x, plug it into the original function. Excuse me, I want to plug in the value there, so I'm going to plug in the 3 numbers. So we've got f of negative 2, f of 0, and f of 2. Okay, those 3, the value of the function, the biggest one is going to be the absolute max, and the lowest one will be the absolute min. So plug in negative 2, I get negative 2 cubed minus 3, negative 2 squared plus 20, which is negative 8 minus 3 times 4, that's minus 12 plus 20. That equals negative 20 plus 20, which is 0. So we've got the point, we've got one value is 0. Plug in 0. We get 0 minus 0 plus 20. We've got equals 20. That's another value. Then we got plug in 2. We got 2 cubed minus 3, 2 squared plus 20, which is 8 minus 12 plus 20, which is minus 4 plus 20, which is 16. So these are the 3 values. 0 is the smallest, 20 is the largest. Therefore, absolute max is 20 at x equals 0. And absolute min, that's saying the largest and the smallest that this function ever gets, so it's the y value, is 0 at x equals negative 2. Questions at all? Again, if you were one that included negative 2, negative 1, 0, 1, and 2, I took up something off. Don't include all the numbers, just the endpoints and the critical numbers. You're going to have problems that we're going to be solving later and in Calc 2 that are going to require you to, you're going to be glad you're just doing the endpoints and the critical values in between. That's it. Okay? The last thing I want to do, let's get through this before the class resolves here, is number 3, which is, yeah. Let's do this. Got to get going. Okay, so number 3 is the L'Hopital related stuff. Okay, evaluate if possible. And I said L'Hopital considerations because one of them, you couldn't use L'Hopital. It wasn't appropriate. So this is number 3a, is the limit as x goes to 0 of 5x minus sine x over x. First, several of you didn't do this, okay? Most of you did, but there were more than a handful of you didn't do this. Plug in 0, see what you get. I get 0 minus 0 over 0, 0 over 0. Yes, L'Hopital. So that means this limit is equal to, the equal sign is important and the limit is important. X goes to 0 of the derivative of the top over the derivative of the bottom. A few of you use the notation that you took the derivative of the whole thing. And the derivative of the whole thing is the quotient rule. That's not what you did. You did the derivative of the top over the derivative of the bottom. Derivative of the top is 5 minus derivative of the sine is cos, and derivative of x is 1. So that means, so now we plug in 0. That's 1 on the bottom. So all we've got, plug in 0, we've got 5 minus cos 0 over 1, which is 5 minus, and there were a few of you that just automatically said cosine 0, 0. And it's not. You got to get familiar with it. Until you are, you plug it into your calculator. So the answer is 4. Plugging it in to find, plugging in 0 to see if it's a L'Hopital moment, and then following through to make sure you get the correct answer for trig functions, okay? The answer is 4. All right, questions? B. All right, B. Lim as x goes to 0. No, of sine x over e to the x. Okay, several of you made a couple mistakes, but you did this part. You plugged it in. You got sine of 0 over e to the 0, which is 0 over 1, which is 0. That is the answer. There is no 0 over 0. There's no infinity over infinity. There's no L'Hopital. The answer to this is 0. All right? So it's a matter of making sure you got 0 over 0 before you do the L'Hopital moment, okay? The answer to that one is that. If you plugged in, if you did your work right, I gave you a little something, but it was totally wrong to use L'Hopital in that problem, okay? So part C now is lim as x goes to infinity, and you need to check out as x goes to infinity, where are each of these going? So as x goes to infinity, x squared goes to infinity. And e to the x, it's getting huge. It goes to infinity. Therefore, we've got infinity over infinity. Therefore, we've got L'Hopital, which says this lim that you are given is equal to the lim, it's equal to, it actually is equal to the limit as x goes to infinity of the derivative of the top over the derivative of the bottom. The lim is important, the equal sign is important. And the derivative of the top is 2x, and we've got e to the x in the bottom. Check it again. We got infinity over infinity. So you do it again. And that's equal to the lim as x goes to infinity of 2 over, it's the derivative of the top over the derivative of the bottom. That gives us 2 over infinity. This time we don't get infinity on top. We got 2 on top. And now this time, as x goes to infinity, we get 2 over, and as x, e to the x, as x goes to infinity, this goes to infinity. And as this denominator goes to infinity, you got a fixed numerator, this thing's going to 0. So that's the answer. You needed to check these situations and take the derivative, but you needed to stop there. There were a couple of you that took the derivative of this again, and you got 0 over e to the x, and therefore your answer was 0, but for the wrong reason. You stop when you no longer get infinity over infinity. You don't take the derivative unless you're using L'Hopital's rule, which requires infinity over infinity or 0 over 0. Okay, questions? Okay, D. We've got, special one, lim. I don't need the equal sign. Lim as x goes to pi of, I've only got a couple more minutes. I got to move through this quickly because I've got to do the last question too, don't I? X goes to pi of 1 plus cos over sine 2x. Okay, so first plug in pi. Okay, and check it out. What do you get? So I got 1 plus cos pi over sine 2 pi. on the unit circle, remember pi is over here and 2 pi is here. So the cosine of over here, that's the x, is equal to -1. So we get 1 plus -1, which is 0 on top. And on the bottom, we get the sine of 2 pi, which is 0. So we've got 0 over 0, therefore L'Hopital is appropriate. So this equals the lim as x goes to pi, the derivative of the top. A most common mistake on this derivative was people got 1 minus sine on this. Okay, several did. Okay, you left the 1. The derivative of 1 is 0. So this ends up being just minus sine x over, and on the bottom, the most common mistake here was you didn't use the chain rule. So you got to take the derivative of 2x also. Derivative of sine is cos 2x times the derivative of 2x is 2. So that equals, and as limit goes to pi, we got negative sine of pi over 2 cos 2 pi. And the sine of pi, pi over here, sine is y, 0. We got 0 on top. Cos of 2 pi is over here. That's 2 times 1, which is 2, which is 0. So that is the answer and how you work through it. Okay, listen, we've only got a couple minutes. Let me really quickly go through number 4. This is the one most people got correct. So I'm just going to move through it briskly. Number 4 is the situation where you had this against the wall. A couple of you made the mistake of you did 4 sides and you did 2x plus 2y in that bit. This was a wall, so there's no fence needed there. So we've got fencing equals 2x plus y, and that equals the total. So there's one equation right there. The other equation is area, which is x times y. X times y. And therefore, we got to get this in terms of just x, solve for y. So we get y equals 1600 minus 2x. Therefore, a equals x times 1600 minus 2x, which is 1600 x minus 2x squared. There is your area function in terms of x only. Now, take the derivative. 1600 minus 4x. Set it equal to 0. 4x equals 1600. X equals 400. And then we got area equals xy. Area equals 400 times 800 equals 32 and 4 zeros. Whoops, I did 5. Yep. And that's going to be area, so it's in feet squared. Max area is 320,000 feet squared, period. All right? It's 11:50. If you got any questions at all, feel free to get back with me. Let me know and holler, okay? Do well. Got a question at all, Kristen?
No, I don't. I'm about to leave. Thank you.
Okay, great. And any part, notice the details that were a little different. You're factoring. You lost out a couple. You lost the zeros on the first 2 problems, you know?
Okay.
And make sure you catch that. That's definitely going to be on the fine. It's going to follow you all the way the rest of the exam, okay?
All right.
Be well. Hope you have a good day.
You too. Thanks.
Thank you. Bye-bye.